Recording is on.
Awesome. Okay. Hi, everybody. So, here in today's sessions, we are discussing deeply about the binary search. We are discussing about tree problems. We just discussed about different types of trees, binary trees versus binary search tree. What is the main difference? Which is like all left nodes less than or equal to n, which is root, and all the right nodes should be greater than n. That's the main condition or the ordering property of binary search trees. And we also discussed about complete binary trees and final full binary trees and perfect binary trees. These are different small definitions about the binary trees, different types of binary trees. And now we are at the discussing about the binary tree traversals. So this is very basic question. There will this like binary tree traversal. There are three types: in order, pre-order, post order. So simple way to remember is in means the root will be in between the left and right. So you are processing left subtree and then root and then right subtree. N means root. Okay. So pre-order means before anything. That means you need to process the root first before processing anything. That means processing in the sense, in a basic terms, just printing. But in the processing means it could be anything. If you are thinking each node as an employee object, you are processing, you are calculating something on the employee object. Let's say you're calculating a bonus. So you're processing the root first and then go for the left subtree and then right subtree. That is the pre-order. Let's say post order. Post order means you don't process root yet. You will process the left subtree and then you process the whole right subtree. Once you completed that, you need to process the root. That is the main condition. So in means in between, pre means it will precede, the root will precede the left and right subtrees. Post means like root will be after processing of all the nodes. So that's the main easy to remember. N is something, the place of n decides when to process the root node. Okay, so I'm going to discuss with an example. So here is the example I took here: a, b, c, d, e, f. So we started at a, but what we did is, we before processing a, we need to process the left subtree, which is b, d, e. And before processing b, we need to process d and e and then b. So that's what we are at here. D completed and then root completed and then right completed. Now you completed this whole left subtree. Now what we need to do? What is the next one? Can anyone guess? As per the in order, you completed left subtree. Now you are at the, again you came back to the A, because you completed left subtree, right? So now are you going to process A or are you going to process the right subtree of A?
Process A and then the right subtree of A.
Exactly, because that is what in order is saying. In order is saying once you complete left subtree, process root node. N means root node. So processing in the sense, in the current algorithm, we are just displaying the value. We are not calculating profits. We are not calculating bonus for this employee. Let's say these are the names of the employees. We are, if you are processing something else, you will do your actual algorithm, like processing of the profits or bonus or whatever you want for this employee. At this point, we are just printing the employee name. Let's say A is the employee name. So we printed A. So now we need to process the right subtree, right? The same algorithm works, right? So when you go to the right subtree, now I am at this position. This is the right subtree, C and F. So before printing or processing C, what I need to do? I need to see, do we have any left subtree for C? There is nothing like that. So, okay, then simply put C, and then do we have any right subtree for C? Yes, we have it. And before processing F, we need to see, do we have anything left? Do we have anything right? No. Then, so this is full in order processing. So it's always like this. Just imagine this particular diagram. Very easy to remember. Like at any point, like you have three things, right? At any point you have three things. You always do this like a parabola kind of thing. That means you start from left and complete the route and go to the right. This is a kind of a diagram representation of it's easy to remember representation of in order. So start from the leftmost and process the root and then go to the right. Same thing for the next level and for the top level. So we just did the same way, right? We did this, and then we went this, we printed this, and now we came this, and again we have to do this, but there is nothing here, so we did the same thing. So it's just so if you want, this is the way. In every place, again this way, every level again you process the same way. Is that easy? Is it easy to remember? I hope it is. So now let's look at the algorithm for this. So what are we, as I already revealed the secret here. So before processing something, we are processing the rest subtree with the recursion here. This is exactly the recursion works, right? So you will put aside. So you want to process, you started at A, but you are putting A at aside and you are working with the left subtree. Before you working with B, you're putting that aside and you're working with this left subtree. That is called recursion, right? Recursion always like it will call the same function, you know, from the same function, right? You call the same function. That's what we do here in the in order here. So here is the in order. Now why I put the post order on the top? Here is the in order. See this? So we will process the left subtree. So um, first recur on left child. So you started at node. So node could be root. First time when you are calling this method, it will be root. But if the root is null, no need to do anything, just return. If the particular value is null, no need to do anything. So that's example like if you are looking for the child of D, it is null. There is nothing here. Just return and it will take care. So that's the base condition. Now, so if it is not null, that means A. Let's say we got node equal to A. What we need to do? We don't want to print A. We want to process the left subtree. That means call the same method, print in order. The same method here, print in order with the node of left, node dot left, right? You already know the basic representation of the node here. So node represents the a particular node in the tree which has a key. Key could be integer or integer, it could be character, or it could be the whole employee object. Let's say you want to put employee objects in a tree, right? It could be the whole employee object. So in this situation, in this particular program, we are just putting just integer value here, and it has two things, right? Left and right. These are the two pointers which points to the next node of this particular node. So now what are we doing here in the in order? We are calling the same method with left, and then if this process complete, that means you completed the left subtree of this node. Now simply print the node dot key. So print the data of the node. Now once you print the data of the node, call the same method with right, node dot right. Just 3 lines, but rather than just memorizing, just understand the concept why we are calling in this particular way. It's basics, I know, but I hope most of you guys already looked at these kind of in order, p order in our college days itself. We will practice this, right? So but if you want to look at the representation, the graphical way how this works, this is how it works. So this is in order, and I will skim to the next one, which is like same thing like pre-order, post-order. So we will go through the next. Is there any questions on in order?
No,
No.
Suresh.
Okay.
But while executing, it will apply a call stack, application call stack, until the each node is printed under a root node, right?
Exactly. That's what happens. So basically what happens is it will put the values aside, means it will put in a stack. So recursion always uses stack, right? So it will put the values, it will put the value of A aside in a stack, and it will resume when it completes the left subtree. So that's what happens. So in order is like this one, right? As I said, in order, left, and then main node, and then right. So that's what happens. So and yeah, I can put a breakpoint and show how it works, but let me explain the other two as well. So very quickly. and then I can put a breakpoint here and I can show to you. Okay, now let's see.
Suresh, can you tell what will be the time complexity?
Oh yeah, complexity. That's good. Yeah. So complexity here. Can anyone tell before I tell this?
N O of n.
Exactly. That's a good. So okay, I will let you explain why it is O of n. Why it is O of n?
Because we are uh, going to every node, each and every node in the queue once.
Yeah. Yeah. Yeah, that's exactly right. So O of n is because we are reaching every node. So in order, like complexity is basically like most of the times complexity for like finding an element or something. If you want to find an element, let's say if you want to find element E, there will be a lot of ways. But here you are printing all nodes. The requirement says you have to print all the nodes. So there is no way you can escape or skip any node. But so it's order of n for sure. But if you look at it, I'm thinking it could be more than n, like a real complexity, right? You are touching a more than once. So it's a really good question you asked, Mega, because I'm thinking it is also order of n, but it could be more than n. But if it is more than n, we don't care, I guess. Like even in it may not be n square, but I'm sure. Let's find out. It's a good question. I never thought you know complex
O of
complexity.
n plus some constant is O of n. Will it be right, Suresh?
Com-
And we are assuming, since we are using recursion, we will be stopping at every function call and then
mhm.
resuming it again.
Yeah, uh, under algorithm. Yeah, so I'm thinking like you're not touching every node one. You're touching every node more than once. So I'm just searching here if I can find a good way. So complexity of shit. Something else. Complexity of in order traversal. Why it says in order. Yeah, complexity of in order traversal. Yeah, if the tree has n nodes, then each node is visited only once in order traversal, and hence the complexity is order of n. Here, the input is the terms of number of nodes in the tree, and hence, so basically it says order of n, but it's not like you are visiting more than n. No. Yeah, actually I'm wrong. So we are visiting each node only once. See, we are like we visited node A, but we did not process A at. We are putting aside in a stack, and then we are visiting this. We are processing the left node, right? So we are not coming to A again and again. We are just put aside. We put the things aside. So definitely it is order of n. So we are not coming back to the A. There is no way back because there is no back. They always like down, right? So the control is still there in a stack, and then it will process this one. So now in order to process this one, again b value, put it in a stack. A will be here, and then A will be here, and B is on top of A, and then it will go to the next one. So it definitely order of n. You are touching each node only once. So basically, if you look at this algorithm here, right? So this particular in order with a particular node A or B or any of these, like let's say C or F, it will call this particular method only once. You never call print in order with A again. It will call only once, right? So this particular algorithm executes for every node um, at least only once. So that's why it is order of n. So is it clear, Mega?
Yes.
Yeah. So but this is good question. I was little confused. Like, are we visiting more than once? But no, actually, we are not visiting any node more than once, we are putting aside before processing it. We are crossing the left, subtree, and then we are visiting root. So it's order of n. I think it's the same for every other algorithm as well, like print, pre-order, post-order. So, but anyway, that's a good, very good question. So now, do you want me to go through the pre-order? It's pretty much same, but I will explain if it is required.
how we can calculate the space complexity in recursion?
Space complexity in recursion here. Yeah, how much space
Will
we
it be
want?
O1?
No, it may not be O1 because it could be, again, it could be order of n as well, or it be little. Yeah, it is order of n because um, no, it could be order of log n, I guess. Order of log n. At any point, let's say, let's put it in a stack. That's a good question again. So let's say A, B, C, D, E, F, right? So how much space we want? At any point here, let's see. We want to process A, but before processing A, we want to process the left subtree, right? So that means we want to put A here. Now, before processing this, we want to put B here, B on the stack. And then we will process D. Before processing D, we want to put D here. Now let's look at here. Once you process D, once there are no nodes here, you are going to remove the D from the stack and then process the D. And then it will go back here. You will remove the B and then it will process the B. So now you can put F here in place of B. The F will come here because only A is in the stack. F will come here. A, B, C, D, E. Sorry, this is E. Sorry, E comes here, right? So now at any point, look at this. At any point, you don't require more than three spaces in the stack. This is a very good question because it's order of log n. It's called 3 means like 3 levels, right? Let's say if you have something here, let's say if you have k here, that could be 4. So I think it is order of log n, or number of levels, probably, like maybe number of levels. It may not be order of log n. It could be number of levels. So we need just um, we need this we need the stack size equal to number of levels. That's what I'm assuming. It could be wrong, but let's think about and tell me, is it right or wrong? Because at any point you don't store more than 3, right? Is it right? You're when you're going up, you're removing the elements. So we don't need order of n. We never store all the elements in the stack at any point of time. Is it clear? I think your network is showing as yellow. Karanya, is it clear?
No, Suresh. I'm
So what I'm
confused.
saying, it's confusing, right? So what I'm saying is you never put all the elements in the stack, right? So like when the recursion works this way. So if you want to process A, right? If you want to process A, you need to put A in the stack, and then you will process this left subtree. So before processing
This
left
is the
subtree, you
call
want to put B.
stack, Suresh, but for the required output, we have to traverse the whole tree, right?
Yeah, we have to traverse the whole tree, but how much space do you need in the stack? That's what Mega asked about, space complexity.
Okay.
Space wise, the
Okay.
space wise, yeah, like when you are processing the A, you will put A aside and you process the left subtree. When you are processing left subtree, you put the B aside, right? You put the B aside and process this. So when you process D, you will put the D here and see, do we have any nodes here? No.
Okay.
Then you remove the D before printing. That's what happens, right? When the recursion come back to that D, it will be removed because you already processed the left and right of D. You will remove the D and D will be printed, and then go back to B, and then B will be printed, and then before B printed, after B printed, if it will insert E into the stack. I think E will be inserted here, and then when you are processing E, right, there is no other thing. So when you complete the E will be removed, Since you completed D and E, B also removed, and then A will be processed. So at any point of time, you don't need more than the number of levels.
Okay.
That's what I'm saying. So once
Yeah.
you complete A, right? So already B and D, everything already removed from the stack. So that's a very good question. Actually, this is the advantage of group discussion. So this is are the good questions. So we can also look at the online. What online says? Space complexity, order of n. And have you searched for that? The time complexity in the meantime. Time complexity of in-order traversal. Don't know if anybody answered that. I'm just searching along with you. Time complexity of binary tree traversal. No, not time complexity. We need space complexity. I don't know, but figure out. If you find anything, let me know. I'm hoping it is equal to either it will be order of log n or order of number of levels. Yeah, I don't think order of log n. It will be, I think, number of levels equal to number of levels. Yeah, tree. The reason you get here is that your equation complexity is
Yeah, it's
incorrect.
height of the tree.
Oh, did you find already? Yeah, height of the tree. Did you find it?
Yeah, and Stack Overflow.
Oh, nice. Yeah, send me that link so that we'll read it. This is really good questions, Mega. Yeah. Yeah. That's the main thing for in order. But let's do for yeah. I think you posted here in the chat. Is it the same thing I opened or is it a different one? Probably. Sorry, my internet was ready to say to tell us about the timings. Okay. Okay. Mario, can you hear us now? I hope it is. So, yeah, that's good. Let's look at the other algorithms. You know that, right? Like in order, pre order, and post order. So, now I want someone to tell A, B, C, D, E, F. Soumya or Vinila, can you tell the we completed in order, pre order. We want pre order. So, what is the pre order rule? Or anybody? I don't want to, put it on the spot. So pre-order rule is basically first we need to process the root node pre. That means you are processing the root node first, and then left and right subtree, right? So now, can anyone tell me the answer for this whole in pre-order traversal for this?
A, B, D, E, and
A,
then
B, E, yeah, and then
D, E, and then C and F.
C and F. Yeah, that's it. Yeah, you are processing basically the root and then come back to the subtree and then again processing the
The
root
root,
and
left,
then go
right.
back to the left. Exactly. And then once you complete this, then so you can think of like this. In a diagrammatic, this is in my mind. Pre-order always I will think like this. Start here, complete here, and then complete. So complete the root, complete the left, and then complete the right. So it's the same thing. So when you come here again, complete the root, complete the left, complete the right, right? So that's how it is like this. So you first finish that and then come here, come here. So this is the way I will represent in my mind pre-order. So first the root, root left right. So is it clear the answer, or do I need to explain again in detail?
No.
Vanilla, Soumya, just
It's
want to
clear.
hear. Huh? Is it clear?
Yeah, clear. It's clear.
Awesome. Yeah. Because if everybody clear, we can jump to the next one. So let's go to the last one, which
Yeah.
is post order. Awesome. So let's again I need to let's say I will just say here itself post order. Okay, now I will let another one to say what is the post order for this. Before going to the post order, let me finish showing the post order pre-order. So here is the pre-order. Simple. Just here is the root. Here is if root is null, return. Then, as I said before, pre means first we need to process the root itself. Here is the root node, print the key, and then call the method with pre-order with the left node, and then pre-order with the right node. It's exact same thing. It's a recursion. Yes, same 3 lines, but in a different order, right? So we'll process the root and then call the left and right. So now tell me what is the post order for this one. Post order means left, right, and
And
then root.
root.
First complete the left part and complete the right part, then come back to the root. Post basically is like post production, and like post production. What is meant by post production work? Post production is completed, and then there will be some part after that, right? That's called post production work. Similarly, post order. So we are considering the root after completing a left subtree, right subtree, and then root. So what will be the post order for this tree? Anyone want to say? Vanilla or Mega? You want to try?
F. Uh,
Left. You want to say F? So we
uh,
said left subtree, right? Basically,
yes. So it will be left,
mhm.
root, right. So I will D, E.
uh, not even B, because when you take A, you said don't process A, go to the left. When you process B, don't take the B, go to the left. Because first we need to complete the left subtree. You need to complete the left subtree before processing the root node. It's almost like in order, right? If you look at that in order, what we do, we don't print root. We will process the left, right? So first will be
D,
D, because D there is no left right. So D will be the first one. D, and then what happens?
D,
Right
E,
subtree.
D.
Exactly. D, E, you completed left, you completed right, and then go. I will imagine like this. This is the way. You start from left, and then complete right, and then go back to the root. So if it is pre-order like this, but in the post order like this. So D, E, D, and then what happens?
Uh, C.
Are you sure? Because before
Yes.
before printing C, we need to process left subtree. Do we have any left for C? No. But do we have any right for C? Yes. There is a right subtree for C, right? Don't process C yet. There is a right side of C. So what happens? Before printing C, we need to complete the right subtree of the C. That means we will get F. Is it clear? So basically start from left and then complete right and then root. This is the same direction, right? Start from left, complete right, left, right, and then root. So it will be F and then C. And finally you completed left subtree, you completed right subtree, and then come back to the root A. I think her network is little wacky, I guess. It's showing us right here. Mega, is it clear now?
Yes.
So why I said F and then C? You got it, right? Basically, we need to process the left subtree and then right subtree and then only come back to the root. So that's why this is like D, E, B, F, C, A. So how to do the algorithm? It's exact same 3 lines, but in a different order. So as I said, pre-order, as I said, pre-order comes like root, left, right, and post order is on the top. Post order is left, right, and then root node. So here is the same thing. If node is null, return. Otherwise, process the left first. Once you are complete processing the left, process the right. Print post order node dot right. Once you complete the left, once you complete the right subtree, come back and process the root. Is it clear? I hope it is. Now I can I can run this problem and show. If anyone wants to put a breakpoint, I can put a breakpoint and show how it works. So what I'm doing here is we are creating a binary tree here. We created with nodes 1, 2, 3, 4, 5. So rather than characters up, so we are putting numbers. Yeah, let me run it. So we created this in order traversal binary tree. So here is what we have. Oh shit, I should put it in a tree here. So we have tree like this. We have root node 1, and then left has 2, and left dot right root dot left 3 here, and root dot left dot root dot left dot left, that means 4 here, then root dot left dot right, I think 5 here. This is what we have. Okay, so now what is the in order? Look at the in order traversal on the left side here. So 1 2 4 5 3, right? This is this is pre-order. Pre-order means root comes first, right? Let me try this marker. I think the marker will work. So first root, and then again root, and then 4 5. That is the pre-order. And in order means it starts with the left side. 4 2 5 1 3. And then post order. First complete the left 4, complete the right 5, and then complete the root 2. Again complete the left, completed, and complete the right 3, and then finally print the root. Post order 4 5 2 3 1. Is it clear? I think Soumya left there. Karnya, is it? I think it's clear, right? So I can. So what are we doing? What are we doing? What I did is like I called a tree dot pre-order as a method, and inside that I created a tree dot root. Basically, what I did here is I created a binary tree class which has a root here, and then I created these methods in order, pre-order, post order, and I created these wrapper classes. Basically, wrapper class means like I will simply call tree dot pre-order, tree dot post order, tree dot in order. So it will take care of sending the root. So wrapper class. So in pre-order we are calling this. So let's if you want, if anybody interested, let's put a breakpoint and see the stack trace, how the stack comes here. So
Yeah.
print in order. Let's talk about in order first. In order means first we need to process the left, and then process the root, and then process the right. So let me do that in order. That means let me comment out the other things. So we will just focus on in order. Let me write start debugging. I want to increase the font. I don't know how to do that. There will be some key which I forgot. Okay, now here is the in order. If I continue, where is that? Yeah, continue. Yeah, see, first one is node. What is the node value here? Node is 1. So we are at this location, we are processing 1. But before processing 1, what we need to process? We need to process left subtree, right? So now what happens? If I continue, See, we are calling the same method with 2. So let's continue. So come back here. See, if you look at the stack trace, call stack, see the call stack. It's already here. So call stack main is here. In order with one in order with node is here. There is one more in order created with a different node number 2 in the call stack. We have those values. So now now what happens? The node value is now the node value is 2. 2 has 4 and 5. So before processing 2, we need to process the 4, right? So that's what happens. If I continue, so now we need to process node dot left, which is 4. We have 4 here, right? So before continuing with 2, before printing 2, we need to process 4. So we are calling 4. So now what happens? If I continue, now 4, we are at 4, node equal to 4. Now let's come back here. Now 4 dot left. 4 dot left is null, but we will call with null, no problem. That's what happens, right? So now 4 also put aside, and then we'll go here. Now see what happens. Now node equal to null. That means you are going all the way to the left of 4. There is null here, nothing here. Now return. No need to do anything. Now if I return, what happens is the call stack will come back to the situation where node equal to 4. Now you are printing 4. That is first time you are printing 4. First letter print was 4. Now what happens is node again, like right. You are processing the right. There is no right for 4. Come back. Now you are at the node number 2. You completed processing the left of 4, and you processed 4, and you processed right of 4, which is null. Now you come back to the root, which is 2, right? Now 2 will be printed. Once you printed 2, what we need to do? We need to process the right of 2, right? Now right of 2 is 5. So let's process 5. Now before processing 5, we have to process the left of 5, which is null, and then 5. Printing the 5, and then process the right of 5, which is null. Now you completed with 5. It will print the next number, which is 1. So is it clear? That's how it goes.
Yes.
It processes left and right, and then it processes the left, and then root, and then right. So it will go further. So that's how it is. So at any point of time, look at here. At any point of time, the in order is max 3. So now we are at node. Where are we? We are at 1. We are at 1. See, only 3 nodes, right? So that's how it is. I think the max is 3. Number of height of the tree is the space complexity. So anyway, so now I will remove these breakpoints and show you this. Yep, see 4, 2, 5, 1, 3. So 4, 2, 5, 1, and then 3. So it will process that way. Left, root, right. Left, root, right. Cool. Is it clear?
Yes.
Awesome. So I thought of covering 2 problems, but because of the time compress, it's almost like 10 o'clock. So I will tell you the problem. Think about it. If you can find, maybe if you can find online, you can see the code. Otherwise, try your own. So here is the problem I want to discuss next week, probably. Zigzag problem, zigzag. So basically, trees like this, A, B, C, D, E, F, G. So what I want to do is I want to print level by level, not level by level. It's kind of, it's a reverse. I want to print like this, A, and then second level print the reverse way, C, B, and the third level print this way, D, E, F, G, and the next level print this way, K, J, I, H. So
Yeah,
um,
I saw this problem and came up with a vague solution.
big solution.
Yeah,
Nice.
I don't know it's right and I haven't implemented it.
Very good. Try. It's very good actually. Good problem. So basically, what are we doing here is, so we are doing this way, and then second time we are doing this way. Again, third time this way. So it's like this zigzag. This kind of thing. So you're going this way, and then second time you are going the reverse way. So that's how it is. So try it out. It is interesting. It's not a big algorithm of predefined algorithm. We might already hear like breadth first search, depth first search, and all of those things. So we don't need to do any of those. It's just a basic algorithms, which we can use existing data structures which we already covered so far. So think about what are the data structure we covered. Think about these linked list strings, arrays. Can we use any of these, or is it something any of these will be helpful? The loops, conditions, recursion, stacks, queues, hash table. These are the basic data structures. See if any of these will be helpful for solving that algorithm, and I will explain next week. Okay, is that
Yeah.
good?
So,
Yeah.
problem is depending on the levels we process, right, Suresh?
Yeah, we
Yeah.
are processing level by level. It's kind of
Yeah.
depth first search. Depth means like depth first search means you are processing one level at a time, but not always left to right. In a normal depth first search, or the breadth, not sorry, not depth. It's a breadth first search. BFS. BFS means breadth first search. You are breadth. So level by level. So you're processing first level and you're processing second level of the tree, and then you are processing third level of the tree, but you are processing in a different direction. First time left to right, and second time right to left, for this right to left, and then again third time left to right, fourth time right to left. So it's like alternate directions, right? Maybe I should explain the level by like BFS before doing this. Maybe just how to do this, like A
Yeah, I
and
thought
then
of the
B,
same.
C. Yeah.
But the only thing is the same in order, pre order, post order function I wrote.
Mm-hmm.
With that, I just passed the level, the each the root. The first I passed the level with the root in the function.
Mm-hmm.
So for the next recursive call, it will increase it level
Yeah.
and let the stack or arrays
Yeah.
be there in the first place to push all the uh,
Exactly.
numbers in it. Yeah,
Exactly.
that's
Yeah, that's a good approach. Actually, that's a good approach. Did you get the final answer?
no, I'm implementing it now. Actually, I'm
No.
going to do it
Yeah.
now.
Go ahead. Go ahead. Yeah, I got- So, is it problem? Is it understand? Everybody understood the problem, Vanilla or Mega? If you want to try, just want to make sure you understood the main problem here. The problem is we want to print in different directions, each level in a different direction. So for the output of this one is like this, right? A, and then and for the second level we want to print like CB because it's in this direction, right? And then for the third level D, E, F,
Yeah,
G,
G.
something like that. Yeah. So it's going in a same this direction. So cool. Maybe next time, next week, I will explain normal breadth first search, like every time going the same way, and then I will explain this problem. Let's say normal breadth first search is like A, B, C, D, E, F, G. Just going in as all going in as normal directions. How can we do this? Just print breadth first search each. It's not searching breadth first algorithm. You are not searching for a node, you are not searching for D, you are not searching for G or anything. You are breadth first, um, list of node, or level printing, level order printing, or there are different names for this. You are printing the tree in a level by level, first level, second level, third level, right? So this is called breadth first approach, or level printing. So let's do this problem and then think about how to do this problem. This is a little tricky, right? So left and right is kind of alternate, but we'll finish this and then come back to this next week, like a second problem, zigzag. Cool. I
Okay.
hope Yeah, I hope it is helpful. So, Mega, how do you feel like? Is it class helpful or any feedback or just want to hear from you since you joined today first time, right? Mega, are you talking? Maybe you're muted, so we can't hear you. Are you there? Maybe she was not there. Okay. How about you, Vinila? Is it helpful? Any questions?
Yes, yes, Suresh. It's good. But I need to have a practice because we have a different in order and pre-order things, right? So I need to remind the flow of things and NLR or LNR. So
Yeah, yeah. Sure. I will send this. I will send this algorithm and links and this technique as well. So definitely these are little bit refresh need to happen. Like we will listen, but again we'll forget every time. If for the after some time we'll forget again. So
yeah, that's
before
what
going to
happened last session. It's so clear again. If I am coming to the order again, I'm just thinking about. So I'll have a practice on these things.
exactly. Yeah. Cool. Nice. Cool. How about you and Mega? I just want to check one more time. Like, can you hear us? Maybe he
I
has some
think her
issues.
internet connection has some problem. She mentioned
Yeah.
it.
Okay. Yeah. Okay. No problem. So let's go ahead and wind up. I think it's helpful. So we'll meet again next week. But if I'm giving a session for them, maybe we'll cancel this time. We will see. I will give you the messages. Yeah. Cool. Okay then. Have a nice week ahead.
Thank
Okay.
you.